All right. Well, I'm sure there'll be a couple of extra people who will wander in as we do our introductions, but I'd like to go ahead and get us started. My name is Kelly Montlacroix. I am a research analyst here at the Water Resources Research Center. I'm standing in for Dr. Magdal, our director today, because she has had a death in the family, and so she is not able to be with us today. So I will be trying to play that role. So I probably won't be able to ask quite the pithy questions, but we'll see. So it is my pleasure to welcome Don Gross to come and give a brown bag with us here. He's going to talk today about the Colorado River Simulation System, overview and use in planning and operation of the Colorado River. And for those of you who have never attended a brown bag before, what we usually do is we introduce the speaker, and then we'll go around the room and quickly introduce ourselves, your name and affiliation, just so that we have an idea of who all is in the room, and Don knows a little bit about his audience. So Don Gross has more than 40 years of experience in water resources planning and management in the Southwest. He is currently a water resources engineer with the Arizona Department of Water Resources, Colorado River Management Section. He is involved in numerous aspects of the Colorado River, which include supply, water use, accounting, contract, hydrology, Colorado River modeling, and the Central Arizona Project. Don was ADWR's lead technical specialist for the Colorado River Basin Water Supply and Demand Study. Don has been with ADWR for 26 years and has worked in the following areas: water rights adjudications, surface water rights, dam safety, and program management. Prior to working for ADWR, Don was a project manager for the U.S. Army Corps of Engineers, Los Angeles District for 16 years. He was responsible for water resource planning studies, including the Phoenix Urban Study, the Las Vegas Wash and Tributaries Water Resource Study, and the Los Angeles County Drainage Area Study. Don was also the Corps' lead project engineer for the Central Arizona Water Control Study, resulting in the construction of Plan 6, which included dam safety repairs to several of the Salt River Project's dams and the construction of the new Liddell Dam. So without further ado, let's go ahead and go around, and we'll start here at the table, and then we'll go around the outside. And as I said, my name is Kelly, and I work here at the Water Center.
Hi, my name is Win. I'm a grad student in Soil Water and Environmental Science Department. My dissertation research is also related to mapping the riparian vegetation in Colorado River in the Grand Canyon area. So that's why I want to see this topic today. Yeah.
Norm D. Weaver with the Intertribal Council of Arizona.
Trace English, Sustainable Tucson.
Roy Woodruff at Castle. Northern River, Castle.
Michael Garcia, retired professor. Arlene Skadden, retired.
Keith Sklar, I'm a geologist and consultant from Tempe. Bill Benson, retired.
Bruce Billings, UWAC.
Julia Resnick, U of A Office of Sustainability. Elliot Tapia, graduate associate at the Water Center here and PhD student on the Advanced Department.
Carl Plus at Geosciences, U of A.
We'll go ahead and start with you, Eve.
Okay, Dee Calper, Bureau of Reclamation. I'm Beth Brandon Newman, here at the Water Center. Deanna Ikea is in the Department of Water Resources. I work for Hi, my name is Shannon Weaver.
Not Jeff.
I'm a professor of environmental.
Nick Elke, and I'm just here, and I want to know, is there a test on this?
But that does remind me, so that
You're really going to show all these slides?
It's in my bag.
but that does remind me that the general format is about 45 minutes. We'll have Don give about a 45-minute talk, and then we'll have about 15 minutes. Huh? About an hour? Okay, about an hour talk, and then we'll have a little bit of time for questions afterwards. Just know that if you need to sneak out at 1, that's okay, because we generally try to keep it to 12 to 1. So, and Don will probably give his contact information if you have any questions for him. So, great, welcome, and
Well, thank you, Kelly, for having me here, and thank you for attending. I'm always happy to present information about the Colorado River because it is one of the largest water supplies we have here in Arizona. A couple things. I have handouts of my presentation, a little history of Riverware, which is the computer platform that's the Colorado River Simulation System, CRSS, and I'm going to be using the term model because I have a hard time saying CRSS all the time. So let's have quite a lot of slides to go over, and I was telling Norm that any one of these topics I could spend at least an hour or more on, because with the Colorado River it's always very detailed on any of the topics. So let's start out here. My topics, I always like to start out with a brief overview of the Colorado River Basin. Then I'll go in a little bit of background on the development of the CRSS model. Give a little peek at some of the intricacies of the model and then how it's used in the Colorado River Basin for planning operations, and then how the Department of Water Resources used it for planning in Arizona. The Colorado River Basin covers about 252,000 square miles, supplies water to over 40 million people, irrigates nearly 5.5 million acres of land. There's quite a few entities that rely on the Colorado River. We have 22 federally recognized tribes. There's 7 national wildlife refuges, 11 national parks, and 4 national recreation areas, and also about 4,200 megawatts of hydroelectric power is generated by the reservoirs in the system. Talk a little bit about the storage because we realize, I think everybody realizes the Colorado River flow is highly variable from time to time. Like right now we're in about a 15-year drought. If you were here in the early 80s, we had quite a bit of flooding along the Colorado River because of the El Nino. So because of that, a lot of storage has been built in the system in the upper basin. This area here, we have about 10 million acre feet of storage, with the largest being Lake Powell, 24 million acre feet. And then the lower basin, our main reservoir for the lower basin states is Lake Mead with 26 million acre feet. So right there we have about 60 million acre feet of storage, which is about 4 years of the average annual flow. In the lower basin, we have Lakes Mojave and Havasu. They have about 2.5 million acre feet of storage. And in Arizona, primarily in the Gila River system and the Little Colorado River system, we have about 5.6 million acre feet of storage. So, I mean, I think we have this storage to try to capture the water and when it's in excess and to tide us over in these drought periods. One of the interesting things about the basin, it's been divided up into the upper basin and lower basin, and that was done in the 1922 Colorado River Compact. And the point that we all refer to is called Lee Ferry, and that's right out of the compact. It's not Lee's Ferry, which is the gauge, which is upstream here about 4 miles. So that's where the compact writers divided the basin, and they came up with, they saw about the time, when they were doing the analysis, they saw that the Colorado River had possibly 17 million acre feet of annual flow. Well, unfortunately, that was a very wet period in the early teens and 20s of the 1900s. So they divided up the basin into 7.5 to the upper basin states, 7.5 million acre feet to the lower basin. And later on in 1944, we had a treaty with Mexico, and that gave Mexico 1.5 million acre feet. So that totals up to 16 million acre feet. So they thought that was adequate enough and maybe even a little more. Now in the upper basin, the 1948 Upper Colorado River Compact divided that 7.5 based on a percentage, primarily based on the amount of watershed that contributed to the Colorado in each state. And actually, Arizona got 50,000 acre feet of an upper basin. So Arizona actually has an upper basin and lower basin allocation. In the lower basin, the 1928 Boulder Canyon Project Act allocated water to California, Arizona, and Nevada, as shown here, which totals 7.5 million acre feet. As I said, the flows are highly variable. This is what we call a natural flow, or virgin flow, if you will, since we've been keeping records from 1906 to 2010. And you can see, as I said, the average is about 15 million acre feet. And you can see the variability. In 1977, we had 5.4 million acre feet. That was one of the lowest flows on record. And even if you go back to the paleohydrology record, it is one of the lowest flows. But then 7 years later, we bump up to over 24 million acre feet of inflow. And that's when Lake Powell spilled and Lake Mead spilled, and we had flooding along the lower Colorado River main stem. And then recently, as I said, we're in this 15-year drought. 2002, we only had 6.1 million acre feet. So you can see how drastically the system changed. And here in the late 90s, we actually had some pretty good inflow, and then you can see how rapidly the system can go. This is another graphic showing our the flow into Lake Powell. And I shaded this area here. This is that 15-year period. As you can see, we've only had 4 years of above average inflow during that time period. And this is this 2002 period. And because you can see the drop from the late 90s. And so that has caused the system to drop overall. And we've seen headlines, Lake Mead hits its lowest elevation in history. You can see Lake Powell, you can see these bathtub rings collapse because of the drought. But we still have 50% of storage in both those reservoirs. And the future supply and demands are uncertain. We don't know what the water supply is going to be like and what our demands going to be. So this is an example here. Here's our water use, and showing that we've actually exceeded it, but because we've had our storage, we're able to meet all our demands. But what are our supplies going to be? So this blue is the bound of supplies, and then we have a projected water demand. This graph is from the Colorado River Water Supply and Demand Study, which I'll talk about in more depth later. And finally, we have what's called the law of the river. This is only a small part of over 50 to 100 documents that deal with how the Colorado River water is allocated, managed, operated. And the point I want to make is that this governs how we run the model. There's a lot of operational things in here that have to be taken into account, especially our latest operational guidelines that we developed in 2007 called the Interim Guidelines for Lower Basin Shortages and Coordinated Operations of Lake Mead, and I'm going to call it the 2007 Interim Guidelines. And these were developed because we saw that drastic drop in the early 2000s. So we needed, and the Secretary of Interior didn't have any guidelines on how to allocate shortages from Lake Mead when we saw that the water levels were dropping. So once again, these are just a small portion of the law of the river. Now I'm going to give you an overview of CRSS, or the model, not going into a lot of depth. If you're really interested over here, I printed out a schematic of the model itself. Even at this large scale, it's hard to read. But we have 12 major reservoirs in here, and there's over 500 different water diverters, both in the upstream and then the lower main stem. So I'm just going to talk a little bit about the background and configuration of the model and some of the operating policies. CRSS was actually developed by Reclamations in the 1970s. Developed in Fortran. One of the problems with that is everything had to be hardwired in. You couldn't adjust how you wanted the operating with going through a lot of effort. In the 1996, Bureau of Reclamation and the Tennessee Valley Authority saw the need for developing a different platform to develop the model in, and they contracted with CADS West from the University of Colorado at Boulder to develop that program. And originally, at that time, they called it PRISM, but then they changed it back to CRSS. And for the Colorado, it's the primary tool for river operations and analyzing future projected conditions. Been used extensively for many environmental studies, planning. Like I said, Arizona uses it. Reclamation has a modeling group that they continually update and try to make the model better. Most of the Colorado River Basin stakeholders actually run the model. Like I said, Arizona runs it, CAP runs it, the Metropolitan Water District of Southern California has a modeler. There's several people in the upper basin that use it. And Reclamation makes two official ones a year, one in January and one in August, to kind of get an idea of how the conditions are looking for the next couple of years. As I said, as you can see over here, and I put on the slide a schematic of CRSS. So if you want to, you can take a look at that. Once again, this tool for long-range planning. You know, what you can do is hold some different variables constant, like reservoir elevation. You know, what do you want to have starting elevation, or several different flows, or whatever you want to do. You can run it and get a range of potential outcomes. And some of the outcomes are like reservoir levels, river releases, river flows in different areas. I'm just going to give a little peek into the model itself. This is an expanded view of the model. I'm going to focus on Lake Mead. The key to the model is what are called objects. You have objects for reservoirs, object for river reaches, you have water diverters, you have data objects. I think there's probably 20 different objects that exist right now on the Riverware platform. So we're going to take a look at Mead. Okay, that's the object. So we have inflow in the Mead and an outflow. We have a diversion for the Southern Nevada Water Authority. So the background to all that object is what are called slots. This is where data can be input. You have data tables in here. Data is calculated. So all that goes into, the reservoirs are the most complicated. They probably have 30 different slots. Some of those slots, there's a lot of different engineering formulas you can use in the background, depending on what you want to calculate. And the other part of the riverware, which I think is a powerful tool, is what I call policy or rules, because that's how we really implement, the law of the river, what goes into that. So this is an example of the rule set that currently exists in the model. And I want to point out here, these are all kind of lumped together. There's 148 different rules just for Powell, because that seems the most complicated. And so like Mead only has 3 rules, and Powell has 25, because there's a lot of interaction between Powell and Mead as per the 2007 interim guidelines.
Question,
Yes.
do those rules change much, or are they reasonably constant?
Well, for example, before we had the 2007 interim guidelines, we had a different set of rules. So they went in, and when we developed those, they were changed to the current format.
Okay, but, I mean, unlike rainfall or something like that, which is more up and down, these should be.
Most of them were fairly constant. Yeah, it's just primarily the Lake Mead and Powell, and maybe some of the upper basin reservoirs. If there's any change in how they operated, we try to reflect those into the model.
So a rule would be some sort of a regulatory, this is policy.
Yes. Yeah. And what I've highlighted here is as part of the interim guidelines, Lake Powell has what's called a mid-elevation release tiers. There's certain criteria for that. And here's an example of a rule. And this is one of the more simpler ones. And I'm not going to go through that, but if you go into these rules, it's like this. And then in the rules, there's actually have some of the text in there is actually a computation. It says go over to this function and calculate and come back. But all these rules have to be satisfied when you do a simulation. So you take one hydrology through, so it has to go through all this logic. Right now I want to talk about the major inputs into the model. Of course, we have hydrology. We also have upper and lower basin demands and initial reservoir conditions, and then the rules. So we talked about the rules, so we won't go into that. So for the initial reservoir conditions, Reclamation also runs a different CRSS model called the 24-month study, which I'll talk about shortly. It projects reservoir elevations, like for January of next year. We'll have a projection. You can put that into the model and start running. Operating policy, right now, like I said, we use the 2007 interim guidelines, at least through 2026. If you can do 2 runs with different policy, the operations revert back to what they were before the 2007 guidelines. And then, as I said, we have other aspects of the law of the river, like we just implemented Minute 319 with Mexico, which has some shortage allocations to Mexico as well as surplus, compact delivery requirements. Hydrology, the main base hydrology that Reclamation uses is called observe, resample, or historical. So we use that 1906 to 2010 period. But also now we can run paleohydrology. So actually researchers here from the University of Arizona Tree Ring Lab have extended the record way back to 762, and they're able to develop what the flow of the Colorado River was from analysis of tree rings. And we've also incorporated what we call downscale climate model hydrology. It will take the predicted temperature and precipitation and convert that into runoff, which gets input into the model. And then demands, we hit the base demands that Reclamation uses is from the Upper Colorado River Commission. Lower basin demands developed by each state, but pretty much Arizona, California, and Nevada are using full apportionment, as well as Mexico. And for the Colorado River Basin Water Supply and Demand Study, we looked at a whole other suite of demands. So you can see so you can take one of these demand scenarios and run it through the model and see how affects the level, say the level of Lake Mead or probability of shortages to Arizona. This is an example of the hydrology. So this is that record, the historical record. And then this is the tree ring record from Miko here, David Miko. So there's 1,200. This has 105 different hydrologic traces or sequences. This particular paleo has 1,250. Reclamation went through and did what they call paleo condition. That somewhat takes the wet and dry cycles from both of these and melds them together. You have 1,000 sequences. And then for the downscale global climate models, at the time we were using 16 of the, I'm going to use this term, CMIP3 from the United Nations modeling, came out with 112 sequences. So you can see you can run all these different hydrologies and see how it affects the reservoirs. Talked a little bit about the upper basin demand. So this is the one that reclamation uses. The upper basin builds out of about 5.6 million acre feet by 2060. And you can see if you look at the historical low, it's much lower. So, and then these dash ones are for the basin study that we developed. You can see all those are still higher than what the historical is. And that has an effect on the outcome of the model, especially for the lower basin states. And this is an example of, as I said, the lower basin states in Mexico are pretty much using the full apportionment. Nevada has 300,000 acre feet. California, 4.4 million acre feet. Arizona is 2.8 million acre feet, and Mexico is 1.5 million acre feet. One of the things that we modelers deal with is you can get tons of output data. And what do you do with it? How do you analyze it? So you can get reservoir elevations, releases, occurrence of shortages. How does the operation affect your diversion and deliveries? We have salinity. There's a portion of the model that deals with salinity, how a lot of these, how the operation affects the salinity. And this is just two examples. I'm not going to get in great detail, but one of the things we look at is what is the elevation of Lake Mead at the end of the year. Because for Arizona, we're looking at, are we going to get a shortage or not? And this is just using percentiles. So this is the 90th percentile, 50th, 10th percentile. And this is taken out of the EIS for the 2007 guidelines. And you can see if you put different alternatives in there, you get different outcomes. So that's the beauty of the model. And then this is an example of probability of shortages to the lower basin. Once again, you have several different alternatives. You can see how they affect the probability of shortages. Yes?
Say percentile, what percentile of what?
It's a percentile of all the values. You can look at all the different values, all the elevations. So what elevations are in the 90th percentile? So we're looking at Lake Mead end of December elevation. So if you have 105 traces, you go in and look at, well, what are the end of month elevations for your period, say from 2010 to 2060, and you can find which ones are in the 90th percentile. So high elevation, like sort of your median elevations, and then this gives an example of how, what is the lower range of elevation. And okay, now I'm going to transition into how the model is used. Really, if you look at it, we have the long-term planning, it's basin-wide over decades, and that's really what CRSS model that we use now. Also have midterm operations. We want to look at 1 to 2 years. That's the 24-month study that Reclamation runs. I'll talk about that. Not really going to talk about the short-term operations because it's more individual reservoir oriented. So let's talk about the long-term planning model that Reclamation and the states run. In the 80s, there was various basin-wide studies that the earlier CRSS model is used for. Actually, in 1995, there was an analysis of the operation. I'm going to Canyon Dam that resulted in the Grand Canyon Protection Act, or was a result of that. I'm going to talk about two, kind of an early modeling effort, interim surplus guidelines in 2001, and then a more complicated basin study in 2012. I just want to give a comparison to how the use of the model has evolved over time. Talk about the interim surplus criteria. Well, why did we do that? There was a need at that time because the reservoir levels were high after fairly high inflows into the system in the late 90s to have criteria to allocate surplus water. The other issue was California was using more than its apportionment for quite a while and was urged to reduce down to their 4.4, but they still wanted to use surplus water. And then Arizona and Nevada were approaching full use of their apportionment. I wanted to use this particular graph because this is the time period that they did the interim guideline. And you can see Lake Mead is up high. And then all of a sudden the hydrology just decreased, and you can see how rapidly Lake Mead dropped. And I don't believe any of the three states took any of that surplus that was identified in this criteria. But I mean, we didn't know. I mean, that you don't know. There were several alternatives evaluated. When you do an EIS, you always look at a no action. And then the basin states in California had several alternatives. I'm not going to go through those. I just want to talk about, well, how do we use CRSS? Well, unfortunately, at that time, not all the basin states or stakeholders were even using the model. It was on an old Solaris platform, if anybody remembers those. The computing power was much less back then. To do one of these runs took 8+ hours to do. So Reclamation, to do a screening of all the proposed alternatives, developed the CRSS, which is a real shortened version of a model to quickly screen alternatives. The stakeholders in the lower basin could run this model and test out alternatives and suggest them to Reclamation. The interesting thing was the policies were again hardwired into that particular model. And any changes, you had to go back to Reclamation and ask them to change it. And then the big model was used to evaluate the final set of alternatives that I showed you earlier. So this is an example of the simplified version of CRSEZ. This ran in about less than a minute on your computer. Now when I run it, I blink and it's done. That shows the difference in computing power. So pretty much simplified, the whole upper basin, and simplified a lot of the inputs and outputs from the lower basin. And just to contrast again, so there's that's what we're dealing with now. So you can see everybody's using this now because we have the computing power is much better. Now I can run this particular model even for 100 years in about 3 hours, which is good. And Reclamation, for the basin study, they had to run, I don't know how many different model runs. I mean, they can get it down to about an hour if you buy enough computing power. Now I want to get into a little more depth about the Colorado River Basin water supply and demand study. I'm just going to use the term basin study. And this, compared to that earlier 2001 effort, this really maxed out the use of the model. I mean, Reclamation really had to go in and do a lot of additions and modifications to do the basin study. And what were the objectives of the study? I think some people objected to it. We're trying to look at future imbalances in water supply and demand for the period from 2010 to 2060. Also, we want to assess the reliability and risks to the basin and its resources. And also, we want to see what can we do to mitigate these supply and demand imbalances. It began in 2010 and ended in 2012. And one of the things which I think is a first for Reclamation, we really looked at a scenario planning process. So what's going to happen in the future? Earlier planning processes, they just took, well, we're just continue along our current trend path. Well, some researchers, I think also from the U of A, developed the scenario planning. So there's an infinite number of paths you can take, and this is what we call the cone of uncertainty. We're here, but what happens out here? Like, we have questions. So we went through a process of developing pretty much demand scenarios. What are those going to look like in the future? So we can explore, what will the future look like. Talk a little bit about the supply scenarios, and I think I went through these. Again, we use the historical, the two paleos, and then the downscaled climate models. And when you look at running all those, okay, so we have for the observed, we have 15 million acre feet mean flow. If you do the paleo, the whole record, the average is 14.7. You do this paleo condition, about 14.9. But look at when we do the downscale, we're down to 13.7. It's about a 10% reduction in the mean annual flow of the Colorado River system. Now for the demand scenarios, we looked at four major areas. What is the current projected? So once again, what does the current path look like? Because at the time we were doing this, we had the downturn in the economy. We looked at it slow growth. Then we said, well, what happens if the growth returns? We had two branches of that. Slower technology adoption, that means, what kind of water efficiency measures were adopted. We had a more rapid adoption of that. And then we had what we call an enhanced environment. We had two branches from that with rapid and more moderate population growth. But these two scenarios had the highest water use efficiency imposed on them, just to get an idea of what that could do. This is a summary of our demand scenarios. So once again, you can see we tried to bracket, although it wasn't as large as I expected, but it ranged between 13.8 and 16.2 million acre feet by 2060. And if you add in Mexico and losses, it's 18.1 and 20.4. So there was about a 20% spread between the slow growth and the rapid growth. Some of the conclusions from the basin study regarding the imbalance, that by 2060, the median supply and demand imbalance was about 3.2 million acre feet, but it ranged all the way from 0 to over 7 million acre feet, depending on, the combination that you use. And that's what I said there. And we've actually had some imbalances that we've seen in the past, but we've had our reservoir system to manage the demand. And I saw earlier, one of the objectives of the study was development. What can we do? What kind of options can we do? So we had a public process where we solicited input from the public and the stakeholders within the basin. We had about 150 options submitted. You can see the little pie chart there. 34% of them related to increased supply, 26 reduced demand, 14% modify operations, and 26% was governance and implementation. That means, well, change the law of the river, or move people out of the basin. We actually have people be relocated along the Great Lakes. So we had to develop what we call portfolios, which is a combination of pretty much the first three there. We came up with 4. We looked at one called Portfolio A, very inclusive, included a lot of the different options. And then, using this Venn diagram, we could see we had looked at one, Portfolio B, looked at long-term reliability for the system. Portfolio C, we're looking at more low impact to the environment. And then, of course, we had the intersection of all three of those, and that became Portfolio D. I mean, once again, if you look at the scenario planning process, you could have a million different portfolios, but because of time and financial constraints of the study, we came to these 4. Once again, we tried to cover the range. This is an example of Portfolio A. A lot of different options were broken out into increments. and when they could be implemented. Like for weather modification, you can do that now. It only costs, $30 an acre foot to do that. And you compare that with, say, down here, a desalinization plant in the Gulf of Mexico, it's $1,800 an acre foot, and you can't implement that until about 20 years in the future. So we had to take that into account, and that's one of the things that Reclamation, working with the RAND Corporation, developed a process to, when we went through the whole modeling, when do we need to implement a particular option. This is another graphic showing how often a different option was implemented. So the ones that are all red, pretty much red or orange, were implemented all the time over the course of the simulation. And the little black bars show when they were initially implemented. So this was all done in the model. This is all output from the model. And the last thing was to look at the reliability. So you have the condition where you don't do any options, you use this hydrology or that hydrology, you put in options. So what is the reliability and the risk to the systems? And one of the things we develop is metrics. Well, how we're going to quantify this. We looked at metrics for all these different resource categories. For example, water deliveries would be how many times Lake Mead could go below 1,000, or the compact delivery requirements from the upper basin to the lower basin, met those sort of things. This as some way to evaluate how the system is doing. I think this should really focus everything. When you go back to the 2001 study, it was fairly simple. So here for the basin study, we had all our different demand scenarios, and then we had 4 different supply scenarios. So you can see all the different crisscrossing of the combinations you can do. Well, then you throw on top of that the 4 portfolios. And then the last thing is there was 2 different operational policies concerning the 2007 interim guidelines. Do we extend those past 2026, or do we revert back to that prior operation? And this is what you get. There was 117,000 traces that were developed by this, and that's what Reclamation had to deal with, is how do you manage and report all this different data. And this is one example. Once again, it's similar to that earlier Lake Mead end of December elevations that I showed. It's showing the 90th, 50th, and 10th percentile. And one of the interesting things is this blue and kind of orange color. Those are the global climate model projections, and you can see they're always the lowest. So it's the lowest in the 90th percentile, here in the 50th, and then really low in the 10th percentile. So I think one of the outcomes of the basin study is if we really are in climate change, it's going to have the greatest impact on the flows in the Colorado River system. This is another way of portraying the data. These are some of the water delivery metrics that we looked at. So we have the baseline condition, and then if you impose the portfolios on them, one of the ones we look at is, say, lower basin shortage. So any 5 years if it exceeds 1.5 million acre feet. So under the baseline condition was 59%, and then you can see the reduction in the portfolio. I mean, there's one whole volume in the basin study that just has all this data, tried to portray it graphically. And this is the main report. You can go to Reclamation's website, and they have this. And I'll show you here, there's, I think, 8 different reports, 9 reports. So as we went through the study and we completed, first thing we developed was the scenarios. Then we looked at, what sort of water supply scenarios are going to be using, water demand assessment, what sort of metrics are we going to be using, develop options and strategies, and finally we combined all that in a technical report. That's about 1,800 pages total. Now transition into, how's the model used in a reservoir operation? Just another comparison again. For the big model, the long-term model, hydrology, we can use 4. For the 24-month study, which is the one we use for our 2-year planning, we get what's called unregulated flow from the Colorado Basin Forecast Center, part of the National Weather Service. We use, for the Upper Basin Reclamation, uses the 2000 Upper Colorado River Commission. For the 24-month study, it's inherent in their flow forecasts. In the lower basin, of course, we have the lower basin states using their apportionment. For the 24-month study, they use the official approved versions. The CRS can be probabilistic. I mean, you can develop probabilities, or you can actually do one sequence. The 24-month study is more just one model run, and that's it. The CRS is rule-driven. 24-month study is rule-driven, plus there's input from the various reservoir operators. And the time horizons for the big models, 15 years or more, and the 24-month study is just 2 years from the present time. It's a little simpler model than what we have over here. The 24-month study is used in the development of the annual operating plan, which is, once again, part of the Law of the River. It incorporates the 2007 interim guidelines for operating Lake Powell and Mead. It's a 2-year projection. Reclamation updates it monthly. And Reclamation uses what's called the most probable forecast from the Colorado Basin River Forecast Center. And then also the Forecast Center develops called the maximum minimum probable flow, and that's 4 times a year. And it contains the 12 major reservoirs in the system. And the key output from this, from the 24-month study, if you go on the Reclamation site, probably like the first or second week of each month, you get a projection from that study. This gray block is the historical, and then this is all the projection. And for Arizona, we're always interested, well, what is the end of December elevation for Lake Mead going to be? Because that is a projection that we're going to have a shortage or not. In this particular one, from the January 2015 study, we're going to be above our first shortage elevation by about 4 feet. But you go in the projection in the future, it might not be that. And some of the graphics that Reclamation produces, this is from the August, which the August 24-month study is the study that's used by Reclamation and Interior to set the operation policy for the upcoming year. So the 2014 set what tier Lake Mead and Lake Powell are going to be into. And they also do this 3 hydrologies again. This is the same thing for Lake Mead. And another graphic of how like we got interim guidelines operate is this chart here. So based on that August 24-month study, Lake Powell is going to be in what's called the upper elevation balancing tier. Lake Mead is going to be in a normal condition. And because of the way the projections are working, Lake Powell is probably going to release about 9 million acre feet in 2015. The normal release is about 8.23 million acre feet. So, the 800,000 acre feet coming down from Lake Powell. And the real purpose of the interim guidelines is really to try to operate Lakes Powell and Mead more in a conjunctive manner than operating one differently from the other, even more as a one reservoir system. So one other thing that Reclamation has been requested to develop by the basin states is we call it a midterm operations model, MTOM. As I said, CRS, we're looking 15 years or more. 24-month studies, only 2 years. So we wanted to have something looking maybe 3 to 10 years out. So Reclamation is looking at this midterm operations model. Should be out sometime this year. Anyway, like I said, we're looking more to have some data 3 to 10 years out, just to get a better view of what the near-term future is going to be. So finally, I'm going to get into how does Arizona use the big model? And you may ask, well, why is Arizona doing its own modeling? well, we assume some different things in reclamation, which we can do being a stakeholder, is that we assume a different ultimate depletion by the upper Colorado River Basin states. Reclamation, as I said, uses the ultimate depletion between 5.4 and 5.6. And based on our analysis, we think the upper basin can really only develop up to 4.8 million acre feet. That's because a lot of projects that have been planned in the upper basin have never been funded, probably never will be. For Arizona, for some of the work we do, we actually run the model 100 years instead of reclamation, which just goes from the present time to 2060. We look at different depletion schedules for the main stem Colorado River tribes. Arizona kind of use a more moderate tribal growth where reclamation has to use this 10 tribes partnership schedule, which is about 135,000 acre feet more. And that's important because that affects how much water supply is available for the Central Arizona project. We also assume a more moderate growth of main stem non-tribal depletion, so the ag users and the M&I along the river. And also we play with whether the Yuma desalter can operate, and that's important because if you operate the Yuma desalter, you can add 80,000 acre feet to the system and reduce releases from Lake Mead, which in turn will keep Lake Mead elevation up, which will help reduce the probability of shortage. Although unfortunately the desalter hasn't been operated very much since it was constructed in 1992. And then here's an example of, so I showed this graph before, here's the projection that reclamation uses, and here's what we use here in Arizona, leveling out at 4.8 million acre feet. And you can still see it's above if you look at the historical, but we're not nearly as high as what reclamation uses. And this is an example. This is a probability of shortage graph that we use, and Deanna and I run occasionally to update our management. You can see the impact of, this is what Arizona assumes for upper basin depletion, and this is what reclamation. And you can see there's probably a 20% difference in the probability of shortage over time. And the reason why it jumps up here is because right now we're in low reservoir conditions, so that's why shortage is looming. What do we use the CRS modeling effort for? Like I said earlier, we look at probability and duration of shortages to Arizona. We do work for the Arizona Water Banking Authority. They're required by statute to firm CAP M&I subcontractors and also main stem priority 4 users along the river, such as Lake Havasu, Bullhead City. We also do firming for Indian. The state is required, as per some of the water settlements, to firm water for the tribe. We look at providing data for some of the department's assured and adequate water supplier redesignation. Provide data for looking at some of our AMA, active management area assessment reports. Also, we look at, if they change the operation of the reservoir system, how does that affect Arizona? And then recently, Deanna had a big part in it, is we were required by the 2004 Arizona Water Settlements Act to reallocate part of the CAP NIA, which is non-Indian agricultural supply. And I'm just going to talk about the water bank and the NIA reallocation. Yes.
So I just want to be clear. So you're talking about all of these, all of those in your previous slide, all of the things that the state does. Are those all based on the Arizona assumptions that you talked about earlier?
Yes.
Okay.
Yeah. Well, we can, we always try to look at a range once again. We can look at what reclamation's assumptions do versus what we used to. I'll show you this in this water bank analysis. We just updated their firming requirements for the water bank last year, and we actually did some mini scenario planning process. We actually looked at 16 different options, and we came out with 3 to provide the bank with a range of possibilities of how much they needed to firm. And you can look at those, but anyway, we try to provide a range of options. And then once again, I use this probability of shortage because that affects how much water needs to be firmed by the bank. And you can see we have this cone of uncertainty. So that's why they selected that. This is not quite the lowest and this is not the highest, but we wanted to select, working with the bank, we wanted to show something reasonable. And this is a result of this. In this chart, back in 1997, they selected these goals for firming for the On River, like I said, Lake Havasu, Bullhead City, and the CAP M&I priority subcontractors, the priority firming, the NI priority firming for the Indian tribe. So you can see the value here, and we ran the three cases. You can see this fell within our bounds. So case 3, we had, that was the worst scenario, and case 1 was the best. So it just gave the bank, the Arizona Water Bank, a feel for how their goals were looking since they were developed in 1997. And for the allocation of that non-Indian agricultural supply as per the Arizona Water Rights Settlement, we just looked at really 2 scenarios for that particular study because we wanted to look at, well, what impacts the CAP supply the most? And that's whether we have moderate growth along the main stem of the lower Colorado River or full use of entitlements. And the reason why I did this because people are applying for this NIA water and it's not firm. It's not like the CAP subcontractor, the M&I subcontractors. It's subject to more shortages. So we wanted to provide information to them whether they wanted to apply for this supply or not. And just using these 2 different bar charts here for the different scenarios, you can see out of the 96,000 plus that Arizona was required to reallocate, so about 32,000 was not very firm. So they had a firm supply of 64,000 under that more moderate growth. Under the more growth along the river, you can see how it was reduced. And also we said, well, how does the shortage, the reliability of that supply look at different time frames? So we looked from 2015 to 2030. So it's pretty firm for that time period. But then as you get out, you can, from past 2031 to 2111, you can see the, you know, your supply isn't as firm as it would have been. And that's my presentation. So are there any questions? I actually did that in less than an hour. Yes.
Last year, Tom McCann presented a report to the CAP board, and it doesn't seem to correlate with this at all. I mean, what I read in his report was that this kind of linear decline in Lake Mead, and given that we've given away more water than we think is there, it doesn't seem like that's going to change much. Can you elaborate on that?
Well, once again, I'm just looking at how the model, you know, how we use the model. But actually, yes, that's probably correct. There is, I don't know if you heard the term structural deficit. I really call it operational deficit. It's been there all the time. You know, Lake Mead has evaporation losses every year, about 600,000 acre feet. And there's system losses. Every time you release water down through the lower main stem, there's evaporative losses and vegetation along the river that uses water. And that's about another 600,000 acre feet. So that's 1.2 million acre feet. So that's the operational or structural deficit. It's becoming critical because now we're in lower Lake Mead elevations, and where it's at, its elevation can drop much faster than when it's up higher.
So I'm confused. We've got these models that don't seem to show